Hello, my dear students. Warm welcome to all of you. We are with physics now. Okay, we'll be talking very seriously about physics now. Okay, myself is Dr. Shobboshachi Shen. I'll be offering you the physics courses, course objective, course outcome. You can see on the screen, and we are in outcome-based education. So every course is mapped with what is its probable outcomes, which I have illustrated later on. Now there are five modules. Now we'll be adapting one by one to each module and explore the world of physics. Now let us explore what is the topic of the day. You should keep one thing in mind, that whatever we teach in these classes, each video lecture is basically a building block of your future engineering courses. Each class is going to give you some fundamentals, some new concept. And if you add all those concepts at the end of the semester, you will get the correct path of entering into your own engineering curriculum, because all your curriculum are essentially the application of physics. Engineering means physics applications. So let us explore it a bit more.
Hello and welcome to class 9 of my physics 1 classes. It has been a very fascinating journey with you so far, and I wish welcome you back again in my class. So far, you have been talking mainly in quantum mechanics 1, where you have been. I told you it's all theory, high, strongly profound theory. A lot of experiments we have to talk about. We came across the experiment of black body radiation, which is wonderfully explained by Max Planck with the wonderful concept of energy can be discrete. Later on, with the photoelectric effect, where energy is also discrete, but there is the energy of electromagnetic wave called the photon concept. Compton proved the same thing. That has been our last topic. Now, today, our main objective of this class is to jot down everything together, because in my class I have been talking about photon concept, but you have got some other courses, okay, like interference classes, diffraction classes, and interference means superposition, okay, where you have been using wave concept. So it's high time that you compare both the ideas and get some more views into it, okay. So it's better that I make a small 5-10 minutes recapitulation of this little journey of how to move from waves to matter. And again, now I'm getting back with the comparison with waves. So let us do that. So that my finally at the end of this class we'll be able to differentiate, or identify rather, some peculiar nature of the electromagnetic wave, or as a matter of any matter or any wave in general. Okay, they have got some special property, so that we'll be able to explain after the class. So this is me, this is Planck, and he is the father. Every day I will keep his picture, okay, in front of you. And this is an experiment of black body radiation explained by Planck. This was a problem of explaining the energy, total energy. Problem was that he could not calculate the E lambda. He did not know have the right expression of E lambda to get it. How do you get it? With Planck you get it. With that third assumption, you can see the energy of the oscillator is multiple of h nu. That is the discretization. That is the quantization. And later on, with the you see, with Einstein changed it. Okay, how he changed it? I have presented it like this. If you divide it with the Planck, with the involvement of Planck, we divide physics in two parts: 1900 before it's classical, post 1900 modern. So objects are of two types. Some of them are matters, some of them are waves. And matters have got certain feature like mass, momentum, size, shape. Waves have got some other feature like wavelength, frequency, and phase. So earlier people thought the classical physics tells two different worlds. For method to learn, you've got mechanics. Best exhibition of material property is the collision, because only matters can collide, and the best exhibition of wave nature is superposition, and wave and matter makes scattering. That all those things I told you. Reflection is an example of scattering. Now these ideas are all classical concept or before 1900 concept. My point was that both the experiments I have taught in your class, if you see the previous video lecture, you realize both of them has told about a departure. None of the experiment, as a matter of fact, you could not explain with these classical concepts that a wave on a matter will be scattering. Okay, okay, you can't explain it. Okay, so what do you do? For example, photoelectric effect. We thought it's a wave on a matter; it will be scattering, but it was explained not with the scattering concept, so your classical physics was failed. He explained this phenomena, all these observation of this experiment of photoelectricity, which I have already discussed in terms of photon concept. So this energy is coming discretely in the form of photons. Photonic energy, photonic mass, we calculated in Compton effect. Photons are making collision with electron, and because of that, electron takes up energy from the photon and ultimately overcomes Coulombic attraction of that particular atomic nucleus and goes out. Okay, so we get the famous Einstein's fertility equation, everything we get it, but the main contribution is that Einstein has got a Nobel Prize because of this wonderful concept that energy is discrete. Okay, now again, if we move forward now to this, so the photoelectricity proves this much: waves can be metal-like. That is the main outcome. My objective is never at this age, because you already know, okay, from your school level what photoelectric effect is. It is my point is to tell you in the present perspective of this table or this picture. This is an experiment which is showing the departure from classical concept. Light is no more a wave; it is showing the property of matter, so making collision, which was further established in Compton effect study. This experiment was discussed just in the previous lecture in detail how it is done. It is done with X-ray as the incident ray, which is again at the end of the day again another electromagnetic radiation. Okay, now again it was X-ray was incident uh, on the carbon atom, electron of carbon atom, and ultimately we thought it's a scattering process, but it is not scattered actually also. But unlike to normal scattering mechanism, you get a change in wavelength. It was explained with the idea of that it's a photon electron collision taking place. As you can see there, nature of collision is elastic, conservation of energy is there, conservation of momentum is there, photonic mass, photonic momentum, everything was calculated. So we have been trying to establish photon always as a matter, okay, as if it has got all the attributes of matter like photon, like mass, photonic momentum. Photon is electron, photonic collision, making collision with electron. So all these things are there, okay? All these things are there. And we applied the conservation theorem of energy and momentum. You can see there. And ultimately, we proved it, okay? And ultimately, it is established that for the same story that electromagnetic wave is a stream of photons. Photons are like matters. They have got energy, they have got mass, they have got momentum. They make collision with electron of the carbon atom. Who collides? Only matter can collide. So therefore, we may say our same electromagnetic wave. I have written light wave there. In general, it is true for electromagnetic wave. For example, in Compton effect, we use X-ray, which is an electromagnetic wave. And for photoelectricity, we will also use visible light, which is also electromagnetic wave. So electromagnetic wave, therefore, in my class, they are showing the property of matters, photons, because they are doing both of them are collision experiment. In both the cases, electrons are colliding with the photons. On the contrary, uh, you already know from your school life or even interference courses that radiation means or electromagnetic waves means, okay, it should have some wavelength, some frequency, some phase. If it superposes, I'll get interference pattern depending on the phase relationship. So all these things you know, okay. So the same light in your laboratory class mainly, okay, when you do laser diffraction, okay, it is showing the property of wave. And now, for example, laser diffraction experiment, which all of you have done or you'll be doing in your normal class. Okay, this is the glass grating, and these are the opaque space of the grating. Okay, you see those gaps are called aperture. So what was happening, you see, in the experiment of your laser diffraction, this was the radiation coming in. Suppose it is passing through with initial intensity I1. And diffraction means if any radiation is incident at the edge of the obstacle, it will get bent, maybe by some angle theta or something, and in the experiment we try to determine it. So similarly, I have shown here with one slit, if parallel beams are coming in, okay, so this is deviated, okay, like this. So this is the what now ultimately these beams do superpose, and because of superposition, you get wonderful pattern, interference pattern, sorry, diffraction pattern. The central maxima, first order, I just said, all these things you have been getting, you have been generating. Okay. So what does it prove? It proves that these in that experiment, what is happening? Lights are red light is coming in. It is moving with some intensity I1, and suppose after bending its intensity has become I2. So two different light waves of two different intensity I1 and I2 are coming in. They are superposing with each other, and superposition means two waves at the same time at the same position, because it's an exclusively wave property. So because of superposition, intensity is varying. Some are intensity is growing, some are intensity is dropping. Now, who superposes? As I told you, wave superposes. So in that experiment, you are thinking the electromagnetic wave as a wave of some wavelength that you try to determine. Okay. So in physics lab itself, you are doing experiment and you're learning experiment where you are taking up or regarding light as a wave. Okay. Now I am shouting, okay, that no. Now light is not a wave, it's a stream of photons. Okay. It's a stream of matter, as a matter of fact. The matter photon makes collision with electron. Okay. So now in lab class, the same me is telling that light is a wave because I have to teach you laser diffraction. In theory class, the same myself is now shouting, no, light is not a matter. Light is not a wave, it's a stream of matter called photons. So the question is that what is actually right? Are the observation made in the practical class is right because what you do in experiment that is also regarded as something correct, or the any change or any uh, the perspective is that uh, what is the in practical class I am telling light is a wave. It is doing superposition. It is making interference. You are seeing that pattern on the screen when you do the practical. Central maxima, first order maxima, second order maxima, all these things you have seen. So what is happening? The electromagnetic wave is behaving like waves in that experiment because they are essentially superposition of the waves, the distribution, redistribution of intensity, and so on. And now, in the Compton and photoelectric effect, you cannot use that theory because if you use wave theory in Compton effect, you cannot explain why electron. Then it will be becoming a scattering phenomenon between X-ray, okay, and atomic system. Okay, then Compton effect should have been a scattering phenomena, but in a scattering phenomena, wavelength does not vary. That is varying, so you could not explain with your classical theory. Even the photoelectric effect. Initially, that also thought that also a scattering phenomena. But again, scattering theory could not explain. You have to use the some other theory. You have to use the concept of photons to explain it. So in my class, whatever I am taught, I am 100% sure I am right. There, there you cannot use wave concept, because if you use wave concept, both of them will become scattering phenomena. And in a scattering, I do not get electron emission. In a scattering, I do not get any modification in wavelength. So in my practical class, light is a wave. In my theory class, I am telling light is a matter, stream of photons. Light is a matter, not light is a stream of photons. Okay, which is having material property, mass, energy, and momentum, etc., etc. So what electromagnetic wave is actually? Is it a wave or is it a matter? In lab class, it's a wave. In theory class, it's a matter. In lab class, you are explaining interference with superposition concept. In theory class, you are explaining Compton effect with collision concept of photons and electrons. And problem is that you cannot use my theory class concept of photonic idea in your laboratory experiment. For example, I try to explain this phenomena as photons are coming in. Suppose these are photons. Okay, suppose these are photons coming in. Now the point is that, so these are all photons coming in. Point is that, okay, photons will come, photons will maybe deflected also, but photons, you see, photons cannot superpose, which is the essentiality of this pattern that you have seen, the central maxima, first order on either side, second order on either side, like that. This pattern you can never generate if photons are coming in, because photons are matter. Matters before superposition, they are not going to superpose. They will make collision. That means if you use photonic theory, if they collide, obviously cannot get the pattern. But in lab, you have seen the pattern. So those spots you have seen. So that means you have seen interference is taking place. So that means superposition is taking place. Who superposes? Wave superposes. So in the lab, you have to shout light as a wave. And you cannot use photon concept there because photons cannot superpose. Opposite is true. You cannot use wave concept in Compton effect. Then you cannot explain the change in wavelength. You cannot explain the electron emission from in photoelectric effect. You cannot do that. Okay, so there you have to use photonic concept. So therefore, light has got a very peculiar nature, dual nature, as you say. Sometimes it is wave and sometimes it is matter light. Problem is that what light actually is. Is it a wave or is it a matter? Answer is it is both. Even light does not know what it is. Sometimes it is waves. If you ask light, how do you say it's fine? Hey, light, what you are you a wave or are you a matter? Light means electromagnetic wave. Okay, it will say, I don't know. In some experiment, I am wave. Some experiments matter, but there is a condition. If I am showing photonic nature, I do not use wave nature, and if I wish showing wave nature, I do not use photonic nature. So that is a condition. So therefore, electromagnetic wave has got a dual nature. Sometimes it is wavy, sometimes it is metal-like, but it cannot show both the nature together. This peculiar behavior has got a name. It is called wave-particle duality in quantum mechanics. Okay. So you see this beautiful picture. It's called, it's a wave or particle. What do you see? It's a wave or particle. It's a wave or particle. Wave, particle, wave, particle. What it is actually? Is it a wave or is it a matter? Okay, answer, it's both. It is called wave particle. You can see those videos also have linked here. Wave particle duality. So if you use wave particle duality concept, okay, that wave particle duality idea, this is the waves and matters. Classically, you know, quantum mechanics. By this photoelectricity has told you waves can be matter-like. Okay, and in nutshell, okay, I am now telling today, okay, fine, no waves, light is photon-like. It can be photon-like. Okay, it can be wave-like also. Light is maybe wave-like in interference, diffraction, etc. No problem with that. But chance that was, which was not never in our discussion earlier, these two experiment is establishing that. That is the beauty of the both. These are all hand-on experiment. You are doing it in the laboratory situation. So both the experiments are together providing that photonic nature, establishing the photonic nature. Okay, so this point is true now. Okay, that no wave has the potentiality of showing the material property, and if it is wave property, then you cannot show the particle property, or if it is showing the material property, it cannot show the wave property. So this statement I have written here, this is the statement of wave particle duality. Electromagnetic waves in experiment like interference diffraction shows the property of waves, and in experiment like photoelectric effect counterwave shows the property of particle. So this dual nature is electromagnetic radiation, as you can see there. Okay, each line is important. Okay. Each line. Okay, that's I've kept it like this. So now this is the dual nature. If you see the same light particle wave. Okay, this is a particle duality. Okay, wave particle duality. It's a wave particle duality. You can see. Now I'll now highlight another funny observation. If you see, I'll try to look at a very simple calculation. Let's you see. I'm talking about some dreaming. What is a dream? Let us dream something. The dream is that, suppose in school you have never told about wave, light as a wave. Like I'm telling light because this is more familiar to you. In general, electromagnetic wave as a wave. Suppose you know only photons. That light falling means photons falling. You don't have any idea even what is called wavelength. So now what would happen is that if I only know photon, I have to define photon with this energy h nu. I have to define photon with its momentum h nu by c. I will define photon with its mass h nu by c square. Okay. So basically, you have defined photon. We have to first define photons. It is what photon is. Photon is therefore is a matter. A photon is a piece of light, I should say. It has got some of the features of matter, like mass, like momentum, like um, mass. It has got some mass, some momentum, some certain energy. Now, suppose photonic energy, as you can see on the screen, according to Einstein's special photoelectric effect, okay, is h nu. And we also know the photonic momentum, as we did a few hours back, uh, is h nu by c. Now we can now just consider that expression of momentum is equal to h nu by c that I calculated in quantum effect. You see, you can manipulate that equation or write down that equation. E is equal to h c by mu. It's c by mu. So what it does, c is equal to nu lambda, as you can see there. So this makes c by mu is equal to lambda. So this makes p is equal to h by lambda, or lambda is equal to h by p. The wavelength associated with a particle of mass A moving with the velocity u. Okay, it's very easy. Okay, if you think only photons, you will say this a photon has got momentum h d by c. So that means I may say now that this is equal to h c by lambda. So p is equal to h by lambda, or lambda is equal to h by p. Now this is a very famous equation. What does it tell? That if a matter photon shows wave nature, its wavelength should be h by p. Suppose I just ask you to dream. Suppose you don't know anything about light waves or electromagnetic waves. You only know photon. So what this little calculation tells me, if you have got a photon, if I've got a photon moving with momentum h nu by c, it should have some wavelength. Its wavelength should be h by p. Okay, which is a wave property. So if photon shows wave nature, which photon is a matter, it has got mass, it has got momentum. It has got energy. So if a matter photon shows wave nature, its wavelength should be h by p. It's a beautiful idea. Now this idea was actually conceptualized properly by Louis de Broglie. Louis de Broglie told, okay, fine, if a photon of momentum h nu by c is associated with the wavelength lambda is equal to h by p. This is not only true for photons only, it is true for any matter, as a matter of fact. Any matter can show a property using this kind of formula. Okay. So what de Broglie has to say, so let us have to discuss it. What de Broglie has to say. You see, this is what a particle rate is telling. Waves can be matter-like. De Broglie is telling that just small calculation, that suppose you only know matter photon, okay, then I can associate it with some wavelength, which is a wave property. So de Broglie is telling, if a wave can be matter-like, opposite should also be true. A matter can also show the property of wave. Okay, that is what all of us were talking about. That a matter can also show the property of wave. And if matter shows the property of wave, that wave is called the Broglie wave. Okay, you can see that a waves can sometimes show material property, that is wave particle duality, and a matter can sometimes show wave property, that is the idea of the Broglie. So that means, okay, that is the idea of the Broglie. That means if you look at this photonic concept, just as I share you now, if I consider any photon with any energy, like h nu by h nu and momentum h nu by c, then I can associate with some wavelength. It tells me any matter photon can be, therefore if it can shows any wave, if it shows wave nature, its wavelength should be equal to h by p. Same story. So if all of them are telling the same word, a matter like photon can show, if it shows wave nature, it should have some wavelength. Lambda is equal to h by p. Okay. So now this idea was generalized by de Broglie, that any matter, as a matter of fact, can show a property. If photon as a matter can show a property with wavelength h by p, any matter of mass m can show a property. Okay. So what de Broglie has to say, we'll discuss that, okay, in the next discussion, next lecture. Okay. The hypothesis of de Broglie. So wait for that. Thank you for your cooperation. Because the moment de Broglie comes into picture, life is going to be very difficult. Okay, many calculations, many new concepts will come. Because ultimately, in future also you have to work with de Broglie. Okay, we'll do that. Thank you for your cooperation.
Like a bird on a tree, I'm just sitting here. I got time, it's clear to see. From up here, the world seems small. We can sit together. It's so beautiful, you and me. We meant to be in the great outdoors, forever free. Take a step back to see the truth around you. From a distance you can tell on a tree. I'm just sitting here. I got time, it's clear to see. From up here, the world seems small. We can sit together. It's so beautiful, you and me. We meant to be in the great outdoors, forever free. Sometimes you need to go and take a step back to see the truth.